works. Okay. Hello everyone, I'm Feng, and today I'm going to talk about how we apply deep learning for image analysis in digital pathology, basically to enable automated diagnosis in breast cancer. So first I would like to start with who we are. We are the data science lab inside Science Enabling Units IT. Inside we have 4 different focus areas or 4 different teams. One is natural language processing, and one is knowledge graph, and the other one is deep learning or medical imaging, which is the team where I'm from. And then we also have a team for scalable and cloud computing. So let's start with digital pathology. So what's the difference between digital pathology and traditional histopathology? So traditionally in histopathology, when pathologists want to make a diagnosis, you first need to take a sample from the patient, like a biopsy. Then you have to cut the sample into very thin slices. It's about like 4 to 10 micrometer. And because the sample itself is actually transparent, you can't see anything if you put it on glass. So what people do is you stain it with HNE, hepatocytin and SEO, which is this kind of a blue and purple color, which is believed to reveal morphology in the tissue. Then you put on under a microscope, so the pathology can zoom in, zoom out, focus on different areas, then make a diagnosis of the patient. Then digital pathology, essentially, you still have to prepare the slides, the tissue, and everything, but instead looking at the image, look at this slide under a microscope. You scan the slide with very high resolution scanner. Then you can basically turn that into a whole slide image. Then you can view the image on a computer or share it on the internet or view on a laptop. So basically you can make like a remote diagnosis, etc. So the problem we are focusing on is the problem of detecting metastatic tissue in whole slide images, in particular breast cancer. So on the left you have a whole slide image. Then inside you have like some annotation of 2 metastatic area. Then if you can zoom in, in the area, you can see kind of difference between morphologically there's some difference between the tissue, but normally for a normal person you can't really tell the exact difference. Then this is one basically a zoom-in version where you can see the separation between normal tissue and the metastatic tissue. Then, so in order to develop this framework and to produce some results to test our system, we use the CAMELYON 16 benchmark dataset, which is a very famous challenge in digital pathology. So for this dataset, we have 400 whole slide images. So for these whole slide images, they are stored in 40x or 0.25 micrometer per pixel. Essentially, for whole slide images to work, it basically is an image of multiple levels. Then you can, on the highest level, you have a different resolution. If you go up to level 1, for example, from level 0 to level 1, it will be half the resolution in terms of height and width. Then you keep going. The way they store the image in such format is to allow the pathologists to actually zoom in, zoom out very freely when they view the image. So for this dataset, we have 400 slides in total. Then for each of them, they can be up to 100,000 times 100,000 pixels. Then for the training set, we have 270 whole slide images, 160 of which are normal slides, and 110 of them are metastasis slides. So the task is basically, for the dataset, we were provided with a binary mask to highlight the area of metastatic tissues. Then for the testing set, we have a separate set of 130 slides. So in total, it is over 700 gigabytes data. So in order to tackle this problem, we took approach based on the winning team on CAMELYON 16, which is a team combined of Harvard Medical School and MIT. So for framework, so you imagine you have the whole slide image as the input for training. Then first you have to extract patches of images into either normal patches or tumor patches. So tumor patches basically, those are overlaid with the metastasis mask. So the reason why we're doing this is because even for the most powerful GPU nowadays, you can't fit in the entire slide into the GPU. You can only fit like 64 batch size. Then so we have to create those small chunks of images to fit into the GPU to train the model. So once we have the normal patches and tumor patches, we can fit into a deep learning model. In this case, it's just a standard CNN for classification. Once we train the model, imagine it converges to an optimal solution, then we can basically apply that model to the testing dataset. So for testing, we split the whole slide images into small patches, then predict if every single patch in terms of like probability of the patch being cancer. Then once we have the prediction of all the patches, then we stitch them back together to form the prediction of the entire slide. Then we can visualize it as a heat map to highlight the area of the metastasis. So the patch generation, in order for it to work, essentially we take the whole slide image, we apply a sliding window on top of that. This is done by selecting a particular level, the resolution you want to sample, then also the patch size. So in this case, we select the the lowest level, 40x. Then we basically apply a patch size of 299 by 299 with a center region of interest of 128 by 128. So then we slide the window across the entire slide. But then, because for this step, we actually only generate patch along with the tissue area. So before that, we actually, once we have the slides, because for whole slide image, there in the middle, maybe there's a tissue area, but there's maybe half of that is actually in the background, just white. It doesn't contain any information. So first step is basically then to extract the foreground of the tissue mask. Then we basically apply the slide window along the tissue mask, generate all the patches. So in the end, we have normal patches and the metastasis patch or tumor patches. So in order to improve the robustness of the training, we actually try to improve the variability of the data, of the training data. So we apply online or on-the-fly data augmentation. So on the left side, you can see we apply geometric augmentation whereby by using flipping, rotation, and mirroring, etc. And those are all done in a probabilistic fashion. Then for the color, we first convert the patches into HSV color space. Then we basically randomly augment in the saturation, hue, and contrast channel. So in the end, we will generate a much more rich training set. So hopefully, when we train a model, when we apply to a testing set, it will be more generalized. So in terms of the model we use, is basically we use a state-of-the-art ResNet, like 34, 50, 101, also Inception V4, and also one of the latest one is basically a squeeze and a citation over ResNet. So for the training, we basically took the transfer learning route, where we load a pre-trained model, which is trained on ImageNet. Then we transfer the problem into digital pathology. So basically, in that sense, we basically fine-tune the pre-trained model by using the patches we generate from the whole slide images. So for the training, we can either train the last layer over certain epochs until it converges. And during the training, we basically apply learning rate annealing. Then we can also refine the model by unfreeze more layers, more final layers, then retrain the model until the model converges. So in order to further improve the baseline model, so imagine we train a CNN, it's just standard practice, but we want to further push the boundary of the performance. We apply two techniques that to help the training. So one is basically mining hard negative, where we train a model, then we predict the training set of all the patches. Then we identify the most erroneous patches. So basically the one with the most wrong ones. Then we basically select those ones as a subset of the original training set and form those as a new data set. Then we retrain the model. So we can go through this a couple times to basically a couple of iterations to reach a better model. So the reason why we're doing this is basically to reduce the false positive of the prediction. So in CAMELYON, there are a lot of normal slides. What we observe is like it happens quite often that a lot of normal slides, when you produce a prediction, a lot of them actually contain a lot of false positive. Then another technique we use is called dynamic sampling, which is based on the paper published by Google recently, actually this year. So what we do is this is a probabilistic based technique again. So what we do is we select the tumor category with a probability of p, for example 0.1. Then we use the probability of 1 minus p, like 0.1 again for the normal category. So then we first select the probability for the category, in this case 2 classes. Then we randomly select a slice in that probability with that category. Then the probability for that is 1 divided by the number of slides in that category. Then once the slide is selected, we can randomly select a patch of that category. Then that probability is determined by 1 over the number of patches in that category of that slide. So the reason is to basically we want to ensure there's no or reduce the possibility of unbalanced selection at a slide level. So this is going through for each epoch. So here is the example of the prediction. So this is one of the prediction of the testing slide. So on the left you have the HNE slide as the input. Then in the middle you have the ground truth math. Basically this is the annotation. Then on the right you have the predicted hit map or the probability map of our model. As you can see, these two masks actually correlate really well. So which gave us confidence that our model actually can recognize metastasis in those slides. So in order to evaluate our results, we use 2 metrics. One is for patch classification. It's just standard ROC analysis. Then this is to basically determine the predictive power of each model we train. So basically to find out how powerful are they in terms like predicting patches. Then we also have the official metric, which is called free response ROC curve, which is defined as a plot of sensitivity versus the average number of false positives per slide. This is the script provided by the official challenge organizer. So we basically we produce the results, run through this official script, then produce the results. So for patch classification, you can see the plot here. So basically we train the consumptive V4 and the squeeze and excitation rest next. Then this is the standard. The second one is the standard model. Then we have the one with mining hard negative. Then we have the one with dynamic sampling. Then we have the one model which is basically a combination of the mining hard negative and dynamic sampling. We call it the AstraZeneca model. So as you can see, this particular model produces the best result in terms of AUC. Then for the frog, so initially we trained the model of different architecture.
Can I ask you a question?
Sorry?
Can I ask you a question?
Yeah, sure.
Do you measure AUC on the augmented data set or the original data set?
No, the AUC is measured on the test set. There's no augmentation there. Okay. So for this one, we use the standard like CNN standard technique. Then we produce the results. Then as you can see here, the results are all right, but they're not particularly encouraging. So then we compare with the Harvard results, and it's actually not as good in terms of like when you reduce the threshold. So then, as I mentioned, we combined the minor high negative and the dynamic sampling. Eventually, we managed to basically produce much better results. So for especially the red line, we produced a result which basically outperform both Harvard results. So Harvard, they submit twice. In 2016, they submit the initial method. Then in 2017, they further improved the result, submit the latest one. That's still on the first place on the leaderboard. So for the best results we got, we actually compare with the Google results published in the Google paper. The reason why I didn't put it here, because in the Google paper, they only mentioned the best score at threshold of positive 8, then the average frog score. So in terms of the best at false positive 8, we outperform Google's results, and in terms of the average frog, we are quite similar. So overall, we are on par with the latest Google results. So in summary, for this work, we developed a deep learning-based framework capable of training and testing digital pathology data. Then the model we trained are deployable and show high predictive powers. Then they achieve state-of-the-art performance in patch classification and metastasis detection. So, but interestingly enough, it turns out more complicated models might not give the best performance. So basically, by combining minor high negative and dynamic sampling, we actually achieve better results with like less complicated architecture. So as for the future work, we are in the process of developing a generic whole cell image classifier. Then we also would like to eventually deploy the framework as a digital pathology service. Then, of course, we want to apply the framework to other user cases. For example, we would like to combine digital pathology image data with other patient data to make aggregate diagnosis to help patient in the future. Okay, that's some reference. That's it. Thank you very much. Yeah.
What is the bottleneck for increasing the resolution for Windows like memory?
Yeah, VRAM. Because we were training on AWS P3 instance, which has Tesla V100, which has 16 gig VRAM. That still limits our training a lot. But that's the best GPU you can get on the market. Yeah.
Did you use the ImageNet as the pre-trained
Yes.
for all these different cases?
Yes.
Okay. What's the reason for using a pre-trained model?
No, because so for our training, we use AWS P3 16X instance, which has 8 GPUs. That instance costs $30 per hour. So we can only afford to train like, I don't know, for half day, not like for a few weeks. So that's why we want to, to use structured learning to basically shorten the training time. Okay.
Okay.
Thank you.
Thanks, Feng. Next speaker, Rocío. Yes. Welcome.
Yes. Thanks, but I have a microphone.
You have a microphone.
Yes. Can everybody hear me just fine? Okay. All right, so I'm very excited to be here today and tell you guys all about my work in the molecular AI group here at AstraZeneca. And I'll be focusing on the work I've been doing over the past year as a postdoc here in the MAI group on graph-based de novo molecular design using deep learning. So first, a quick outline of the next 30 minutes or so. I'll begin with an introduction to the MAI group here at AstraZeneca, then discuss some of the previous work that we have done in the molecular AI group, centered around molecular design. Then I'll move on to talking about graph neural networks and how we use them in our group for various different tasks. Then I'll go into some technical details around graph neural networks, and I'll end with some concluding remarks. Okay, so in the MAI group, so the molecular AI group here at AstraZeneca, we work on three main research areas. First is de novo molecular design. We also work on molecular property prediction and synthesis planning and prediction. The goal of the group is to answer the various different questions I've posed here, all using AI methods. So how can we efficiently design novel drug-like molecules? How can we predict different molecular properties? And how can we predict how to best make a compound? So to put it into context, for those who are not chemists necessarily, is here I put this slide that you need to have if you are doing a talk on drug discovery. So here's the drug discovery pipeline. And if you start at the top, we started the drug discovery phase where we have thousands, if not more, molecules that we need to look through to find suitable drug candidates. And every single stage of the drug discovery pipeline, more and more molecules get filtered out, such that at the end we end with a single molecule that will be the final drug that we actually take to market. And in the MAI group, we're especially focused in the drug discovery phase, since there's a lot of data here that is available for us to use, and we're a computational group. So we're especially focused around these ideas of hit discovery and lead optimization, where hit discovery is the idea of finding molecules that will bind to a protein target, and then lead optimization is the idea of taking these hits and tuning them in smaller ways to improve their efficacy. For example, maybe you find some hits that are already patented, or they're too difficult to synthesize, or they're potentially too toxic, then you would want to improve on those properties. And we can put a lot of the work that we do in the MAI group in the context of the de novo design cycle. So we start in the purple wedge here in the top right. We would start by taking one of our de novo design models, and we would use it to create some molecules that we think are going to be promising molecules. And then we'd move on to the next step of the cycle, which would be to score the different molecules using our property prediction models or our synthesis prediction tools. We could then use this information that we learned during the scoring to feed that information back into our models, and in that way create better and better molecules every iteration. So now that brings me back to the three main research areas that we work on in our group, and what I want to do is give you a little bit more details on what we do in each specific subsection. So I'm going to start with synthesis planning and work my way up to de novo molecular design, which will segue into the work that I'm doing in my project. So we have actually about half of our group who's working on synthesis planning and prediction. So I got this slide from Espen. And here, about half of the group working on synthesis planning works on retrosynthesis planning, which is the idea of, let's say you know what compound you actually want to make. So this is just aspirin. This is not something we would want to make. But you would want to use your retrosynthesis models to suggest different possible pathways that you could get to from different available building blocks and different known reactions. And then you would want your model to also score the different pathways to your target molecule so that you could choose the best one. We also have about half of the group working on the inverse problem, which is forward reaction prediction. And here the idea is that you could use the forward prediction to validate proposed reactions. You could use it to suggest optimal reaction conditions and validate a retrosynthetic plan. And I just wanted to highlight some of the work that Amol published I think exactly 1 month ago in chemical science. So if you're interested to learn more about how we use AI in retrosynthesis planning, I recommend you to read his paper. And now, moving on to molecular property prediction. So here, a few key projects that we're looking at in the MEI group is, for example, the prediction of the outcomes of different high-throughput screenings. And here I want to highlight some of the work done by Lorian, who's in the audience, on the identification of frequent hitters and assays. So this would be experimental assays, and the frequent hitters are molecules which are either false positives in your assay or false negatives. And her work was also recently published in CAMELYON. So if you're interested to learn more, I recommend you to look her paper. And then we also have a master student in the group, Victor, who's working with Thierry Couget on the prediction of DMSO solubility. And DMSO is a very common organic solvent. This project has a lot of practical applications because if you could predict if a compound is going to be soluble in DMSO before you actually make it, then it would save a chemist a lot of time. Okay, so finally, moving on to the area of de novo molecular design, which is more of my expertise. Here we have a few, maybe about a third of the group working on de novo molecular design. And most people in the group are, in fact, focused on string-based molecular generation, so that this would be through the reInvent platform. And I'll talk a little bit more about that in a few slides. There's also myself and Tobias, who's a master's student from Chalmers, who are working on graph-based molecular generation. And then Yashin and her master's student Feng from Uppsala, who are working on predicting chemical transformations for improving molecular properties using AI models. So she's also here, so if you're interested, you can ask her at the mingle afterwards, any questions you may have. But for now, I'm going to focus on graph-based molecular generation. So the goal of my project is to use graph neural networks to build novel drug-like molecular graphs. And this is something that we could then use our graph-based models to design promising new molecules to study, for example, in projects. And the idea is that you could save a chemist's time because the computer could come up with viable molecules faster and more efficiently than a human could. The idea is to design a tool that a chemist could then use to carry out their work as they would usually do. So our previous work that we have done in our group on molecular design. So I have here the molecular representations of 3 popular drug molecules. And here they're represented as graphs, but actually one thing that we can do, and is often done in cheminformatics, is to depict these molecules as strings. So I showed here the different SMILE strings. And what you can see is that once you can depict a molecule as a molecular string, that opens you up to all the tools that you have for natural language processing. So except instead of thinking of words in a sentence, you think of the tokens in the molecular string. And what has been done in our group a few years ago is, in Marvin's paper here, they used RNNs, straight on molecular strings, to generate new molecular strings. With the idea being that if you feed an incomplete molecular string into your RNN, it would then output to you the probabilities for all the next tokens, which you could use to complete your string. And because you do this it's a probabilistic model, you have, in this way, the ability to generate new molecules that you actually haven't seen before in the training set. So this has worked surprisingly well. But despite the success of all the string-based methods, the goal of my project is instead to move on to graph-based methods to generate new molecules. And this is because graphs are just more natural representations of molecules. And here I talk about graphs as being a tuple of nodes and edges, where the nodes are, they're obviously going to be the atoms in the molecules, and the edges are going to be the bonds that are connecting the different atoms. So this is a little bit more challenging to build a graph-based generative model for a number of reasons. So the first is that graphs are a little bit more complex representations. So here I show a comparison of what a molecular string would look like for the benzene molecule here, so it's just 8 tokens. And if you were to represent this as a graph, one way that you could do this, for example, is you would need an adjacency matrix that tells you how exactly are the different nodes in the graph connected. So if there's a 1, it means that there's a bond. If there's a 0, then there is no bond. You would also want to use something like a node feature matrix here, which tells you what exactly is the identity of the nodes in your graph. And here I've chosen to use a one-hot encoding of 3 different properties, but in benzene these are exactly the same. One more thing you actually would want to have as well is a matrix that describes what's the identity of all the different edges in your graph. So here we have single and double bonds, and we want to be able to capture those differences. So just also to make the comparison a little bit more fair, when you actually feed in the string into your model, it doesn't look like a string, it looks, you have to turn it into a matrix anyways. So by one-hot encoding all the different tokens from your whole vocabulary of available tokens, but it's still, you can see how this can quickly become more computationally demanding. But there are still some advantages to using graphs over strings. So one of the main advantages is that with the graph representation, you don't have to, your model doesn't first learn the syntax for how to actually create the smiles, and then you don't spend time translating that smiles back into a molecule, but you can instead directly learn the underlying graph structure and connectivity. You can also more naturally incorporate 3D information. And something which is kind of trivial to say is that all the subgraphs of a graph correspond to, it's a valid graph, which not all substrings of a smiles necessarily correspond to a valid molecule. So this has its potential applications. The disadvantages, as I mentioned, is that they're potentially more memory intensive and computationally expensive models, and they're also often more unstable. And I'll come back to this at the end. So now I'm going to talk about graph neural networks, specifically with applications in chemistry. So how do graph neural networks work? I have first a kind of simple walkthrough for anyone who hasn't worked with them before. But essentially, graph neural networks learn to create a graph representation from individual node representations of a graph. And this is kind of a complex way of saying you have your graph representation here, which is a collection of different matrices. And what you could do with a graph neural network is convert all this into a single vector, which would contain all the information that you need for a given task. So let's say you were going to predict certain properties of graphs, then this would have everything that you need to tell the different graphs apart. And I'm going to walk you through the kind of how a graph neural network does this, with again the aspirin example. So here is a molecule that everyone probably knows. It has 13 nodes if we only count the heavy atoms and 13 edges. And if we wanted to turn this kind of into a graph representation to use as input to a graph neural network, we would first have to initialize every single node in the graph with a vector that describes what is the identity of all these different nodes. So I've done this here. I focused on these 3 different properties, so the atom type, the formal charge, and the number of implicit hydrogens. And if we consider only these properties, then all the nodes that I've colored in the same blue colors are chemically equivalent. This is what their vector representation would look like. So it's just a one-hot encoding of these features. And you could actually use this as input to another feed-forward network and get out whatever properties you're interested in, but it's not going to be very good because every single node only has information about itself. So as far as the model is concerned, these 4 carbon atoms are chemically equivalent when in fact they are not. But we can fix that. So we carry out a series of, in a graph neural network, if we think about it in the message passing neural network framework, we can carry out a series of message passing steps which lead to each node sharing its information with its nearest neighbors and them sharing it back to their nearest neighbors. So for example here, if we focus on node 1, it's sharing its node information to nodes 2 and 5. And exactly how it does that is what sets apart the different implementations, and we'll get to that in a minute. But then they would share their node information back, and then we would update our node representation, not just for node 1, but for all the other nodes at the same time. So this is kind of analogous to convolutional neural networks, except that instead of having an image which is a regular grid, we're instead working with graphs which have a regular structure. And let's say you carry out a total of L message passing steps. At the end, you would end up with your final transformed node feature vectors, which each of them would contain information about their local environment. So this is a much more powerful now representation that we have for all the different nodes in this graph.
Can I ask you a question?
Sure.
Is this when you design the data set, or is this part of training?
This is during training.
Okay, so this is instead of backpropagation.
No, you train them using backpropagation. So it will become more clear maybe in a few slides. Okay, I hope. But this is just an example. So once you have your final transformed node features, your final transformed node states, you can collect them using a node order invariant function. For example, you could just sum them together, and then you would end up with a vector that is going to be your graph representation G. And if your graph neural network is powerful enough, then G should be unique for every graph that is unique. And it should also be node order invariant, which simply means that it shouldn't matter how I number the different nodes in the graph, I should still get the same graph embedding regardless. And this graph embedding can then be used as input for various other predictive models. So, for example, a deep neural network, and you can use it for property prediction, which lots of people have done. So these are all references to papers that have used graph neural networks for property prediction. And then, as I'm going to talk about, we can also use them for graph generation. So just quickly to summarize, here I have a scheme of a generative model. So it would involve, we would have some training set that we want to generate molecules like, and we would use it to train our model. We would then use our best model to generate molecules. And if they're promising enough, we could send them off for screening to an experimental lab, or we could then go on to score them, and then use that information to improve our models and go through the cycle however many times is necessary. And I just want to point out that here graph neural networks fits both. We can use it to train the model, and we can take the best one and use it to generate molecules. And also some work that has been done by Edward, who was a master student in our group here at AstraZeneca, was on using graph neural networks for a number of different regression and classification tasks on different molecular data sets. So if you're interested, their work has also recently been published in the Chem archive. No, I think also now it's accepted, but it's at least on the Chem archive. Not some technical details, so I hope equations is okay. But we're interested in a variety of different graph neural network architectures for use in graph generative models. So the thing that all of our implementations have in common is that they all take as input an undirected molecular graph G, which what in practice this means is that we have a node features matrix X and an edge features matrix E, where all of the rows of X correspond to different nodes in our graph. And each of these nodes has associated with it a vector of length C, where C is the number of features we've chosen to encode. And then for each row in our edge features matrix E, we have associated each of those rows with a different edge in our graph. And each edge has associated with it a vector of length S, where S is the number of edge features we've chosen to encode. And here it's usually 3 or 4 because we can have single, double, triple, or aromatic bonds. And I'm going to be talking about all the graph neural network implementations within the context of the MPNN framework, where MPNN is the message passing neural network. And I think it was first introduced here. And what it generally consists of is a message passing phase and a readout phase.
Quick question.
Yes?
How is generative model takes multiple graph as input? Should it be generated as output?
It takes a graph as input, and it will output a graph that has an additional node added to it, or maybe 2 nodes connected. It's coming up also in a slide. But just quickly to summarize how MPNN works is that for all different message passing blocks, you would first want to calculate all the incoming messages into a given node. So let's say here, I wrote this wrong. I meant to put the arrows going into node 1. So let's say we wanted to get all the messages coming into one of our nodes here, so node 1. Node 5 and node 2 would need to share their node information, which we would then calculate using this message function here, which is denoted by the capital M. That message function takes as input your current node states, the node state of your nearest neighbor, and the state of the edge that is connecting your current node to your nearest neighbor. And once you sum all the messages for all the bonded nodes, you then take your messages and you use them as input into your update function u, along with your current node state. And once you calculate that, that allows you to update your current node state to the next one. And you can do this for however many iterations you want, usually not more than 10. What you actually want to calculate from this is your target property, which is shown here as y. And you do this during the readout phase. So once you have your final transform node feature vectors, you will feed these as input into a readout function r. And the idea is that it predicts your property y. And in the context of molecular graph generation, y has to tell us how to grow an incomplete subgraph. And I've split this up into 3 different tasks. So the first would be determining if one should add a node to the graph, determining then instead if one should connect 2 existing nodes in the graph, or determining if instead the graph is complete and you can terminate the graph growing process. And I denote this as here. So this is a concatenation of the fadd, fconn, and fterms to give us our entire target. And just to kind of give you a clearer picture of what this looks like, let's say we have our MPNN here, and it takes as input a molecular graph. What we want it to output is these fadd, fconn, and fterms, where fadd is actually a multidimensional tensor that gives us the probability of adding a new node to an existing node in the graph. And the different indices tell us exactly what should be the identity of that node. Then we have the fconn term, which is a 2D matrix. And this gives us the probability of connecting the last dependent node to another node in the graph. And I also should emphasize that anytime we add a new node to a graph, we also add an edge so that the new node is connected to the remainder of the graph. And then finally, we have the f term here, which is just a number between 1 and 0. And this gives us the probability of terminating the graph generation. And I want to emphasize here that fadd, fconn, and fterm are all probabilities, and together they should sum up to 1. So this is what's going to tell us how to actually grow our graph once we sample from it. So I hope this slide is not going to be too confusing, but in general, in order for the model to learn how to build the different graphs, we actually have to first show it some examples of that. So I'll give you an example here. Let's say we start again with the aspirin molecule, and if the model were to see this molecule, one thing it could say is, hey, this molecule is complete. Let's terminate the graph generation process, which means there would be a 1 here in the f term, and these would all be zeros. We could also then go one step back if we were thinking about the reverse of building the graph. So we remove one node at random, which would bring us to this subgraph here. And let's say we wanted the model to be able to, if it sees this as input, we want it to be able to take us back to the full molecule. So in order to do that, it means there would have to be a 1 somewhere in fadd that tells us to add a single bonded oxygen to this carbon right here. And then all the terms in fconn and fterm have to be 0. And we can repeat the process again. So for the model to know that if it sees this graph, it has to get back to this one, there would have to be a 1 here in fadd that tells us that the next thing to do is to add a double bonded oxygen to that carbon. And you can repeat it until there's a single node left in your graph. And this is how we create the training data. And there's a few more steps, but this is the general gist of it. So the workflow for these whole generative models is we start by pre-processing all the data. So our training, test, and validation set splits, which means we're going to convert our initial SMILES file that contains all the different molecules in our different sets. We first convert it to HDF format for practical purposes. And in this file, we want to have all the possible subgraphs that make up all the different molecules in the training set. So if we were to fragment it, like by removing one atom randomly at a time, until we have a single node left, all of these subgraphs in that trajectory we would save here in the HDF file. And we would also want to save our target probability distribution, which is F add, F conn, and F term, yes?
Yeah, for the training data, in previous slide, I suppose you're creating those based on those assumptions in data structure. But does it have a chemical process sense as well? Is there any physical reality that they can happen?
No, I don't. You mean like something related to an actual reaction that can happen? No, it's nothing like that. It's just I treat the molecule as just as a graph, and I remove nodes mostly at random. Also, trying to keep all the nodes connected and not leaving any disconnected fragments. But yeah. And then once we have pre-processed our training data, we would actually want to train on all our subgraphs here. And we would want to fit to our target probability distributions as I've shown. So we train for n epochs until our model looks converged. We calculate the validation and generation set scores every epoch, and then we save the best model. And we can then use it. We can load the best model and use it to calculate the test set score. And we can generate 2 billion molecules and calculate the percentage coverage of the GDB13 chemical space, which is one of the benchmarks we're using. I'm not going to discuss it in too much detail, but calculating the percent coverage of chemical space would allow us to compare our graph-based method to the previously published string-based methods. And putting it all together here again, back to the generative model I showed earlier. If we have a graph neural network here to train our model, we then take our best model that we trained, and we use it to generate structures. And that looks a little bit like this. So let's say we start from a graph that is a single carbon atom. If we were to input this into our model, we would then get a probability distribution of the different possible actions we can take to grow our molecule. We can sample from this, and then let's say we sample an action that says to add an oxygen with a double bond to this carbon. We grow the molecule using the action we sampled. We feed it back into the model, and then we just repeat this process, adding nodes and edges until the model essentially says to stop. Then we can also benchmark our different models, which is something we're in the process of doing. So I guess I promised some equations. So one of the models that we have implemented uses the GGNN architecture, which is the gated graph neural network. And essentially what it looks like is the message passing function is a feed-forward network that depends on the edge that is connecting your nearest neighbor to your node. And it takes as input the node state of your nearest neighbor. Then we want to sum all the messages incoming into a certain node. And once we've done that, we feed them as input along with the current node state to the update function, which is a group in this case. And that's just the message passing phase. We actually need to combine that with suitable readouts in order to actually predict our target probability distributions. So the GGNN readout looks like this. G is the graph embedding. And how we get it is a product of feed-forward networks. So two different feed-forward networks. This is element-wise multiplication. The first one takes as input your final transformed node feature state for a given node. The second one takes as input your final transformed node state as well as your initial node state. And then you would sum this quantity for every single node in your graph. Then to actually compute your property y, which is going to be the concatenation of the different f add, f conn, and f term that I showed again here, we would get this through different feed-forward networks. So the function we use to compute f add is actually a feed-forward network that takes as input your final transform node feature states, and your graph embedding. So we do this for every single node, and then we stack them on top of each other to get F-add. We do the similar thing with F-conn, but it's a different feed-forward network. And then we do the same thing with F-term, but it only takes the graph embedding as input. So this looks a bit complicated, and we have also tried using a readout function that only uses as input your final transform node feature vectors. So the functions are the same, except here we have a feed-forward network that only takes as input the final transform node feature state, so there's no graph embedding. And the same goes for F-conn, and F-term here is instead now we sum the output of the third feed-forward network that takes as input H of L. But we found that we actually need the graph embedding G in our readout function, otherwise the model has a hard time learning how to generate ring structures, which is very important for generating drug-like molecules. Yeah, so that we have actually looked at a few different readout functions. I won't discuss them all today, but over the last year we've developed our own code using Python and PyTorch. And it has, I'm just going to go quickly because I think I'm getting short on time. But what we're in the process of doing is benchmarking our graph-based method that we've implemented against the string-based method. So one of the benchmarks I mentioned was calculating the percentage coverage of chemical space. How we can do this is by calculating what percentage of an enumerated database, such as GDB13, we can generate with each model. And this is something we can calculate, and working with a master student from Chalmers here on this project. There's two other benchmarks we're interested in, and these would be distribution learning and goal-directed benchmarks, such as using the published Guacamole and Moses, which are open source. And finally, the last benchmark, that would be the task of hiding molecules which we know to be active from the training set, training our model on it, and seeing if the model learns to actually regenerate those promising molecules. So this would be actually the real test to see if, how the model would perform in example projects. So now some concluding remarks. So in summary, I discussed a lot of the work that we carry out in the MAI group here at AstraZeneca. Most of our work focuses on molecular design using deep learning, as well as synthesis prediction and molecular property prediction. I've shown you how we can use graph neural networks for molecular graph generation. We've developed our own Python program, which is soon to be published as soon as we have the results from the benchmarks. So this is what we're currently working on, is benchmarking our GNN implementation against the string-based implementations. And the question that we have is, do graph-based methods better sample the chemical space or not? So now I would like to thank, first and foremost, my supervisors here at AstraZeneca, Ula, Halmin, and Espen, as well as Thierry Cougé and Chris Tertian, as well as the rest of the NAI group for all their discussions and support. I also like to thank my external supervisor, who's Günter Klonbauer, as well as the meetup organizers. I didn't put everybody's name, but I put Eric's name. But thank everyone who organized, and thank you all for your attention. Question?
Yeah, so in terms of the size of the graphs, I mean, how large are they? Does it make sense to add things like attention or convolutions or stuff like that?
Yeah, so that's one of the things I kind of hinted at. These models are very expensive. So there is also some models that Edward implemented when he was doing his master thesis that also have attention, but they run so much more slowly that it's almost not worth to try, because you can maybe better use that time to do a hyperparameter optimization on the less expensive models, and you might find something more promising.
Thank you.
Yes.
So if you make sure I understand this message passing stuff. So is that message passing part of the computational graph that you do backpropagation of?
Yes, you do backpropagation through the all the message passing blocks. So that's why at the end of the day, your graph embedding that you get out from the message passing neural networks, it's very task specific to what you're training, but it's differentiable. So.
Do you
We need the GPU, yeah.
I mean, if the graph structure is done based on the data inputs, then can you pass the batch of data?
Yeah, but that's how we have to train it in using PyTorch. So it has to take in a batch of different graphs, and they're all randomly shuffled. So it's not like the subgraphs corresponding to the same molecule are in the same batch. Yeah, everything, all the training has to be done on the GPU. Otherwise, it's not. You could train on the CPU. I made that an option in the code, but that wouldn't be practical for any large data sets. Your question first?
Why are the generative graphs bounded in size? What keeps them bounded? Is it the classifier? So there's a class within an RNN in the generation stage.
But what do you mean by that they are bounded in size?
It's only the subgraphs that are bounded.
But why does it stop? Why does the generative process stop?
It stops just because the model has seen in the training data that anytime it sees a graph in the training data corresponding to a complete molecule that we haven't yet fragmented in the way I showed, we train the model to terminate the graph generation process. So if your model is not, it also actually has to be bounded. I see now what you mean, because we have to actually pad up the size of the molecules to the size of the largest graph in our training set, so we actually couldn't even generate a graph larger than that, just for practical purposes.
How are you balancing the capacity to predict novel molecules and the capacity to screen them at the end of the day?
Well, at the end of the day, I don't work on actual projects, so this is all developing the tool. This hasn't been used in any actual projects, but there's no experimental component to it. I think if there is promise, then there would be the possibility of exploring that, but that hasn't been explored at the moment. Yes?
How often does it generate molecules you haven't seen before?
It depends when we stop training. So we can keep training, for a really long time, and at some point you just start generating all the molecules in your training set. So this is kind of the big question is when do you stop training such that you balance like the novelty in the molecules you're generating, but you're also risking generating more invalid molecules. So this is the big question. But, okay. One more question?
Can you elaborate when you stop this, like the training? What is the criteria?
Very nice. That's part of what we're trying to actually determine, because I'm balancing kind of I calculate the score for the validation set that I have, and I calculate that every single epoch. So you see that go down, but at some point, and I also calculate the score for the generated molecule set. So at some point, that score keeps going down the longer you train.
What is this score you're talking about?
It's the negative log likelihood for generating the molecule. So every time I sample a different action for, let's say, adding a node or connecting two nodes in the graph, I have the probability for having sampled that action. So it's just the value of that term in the different tensors.
So it's the likelihood of this molecule being able to exist.
Yeah. Well, according to the model, not in terms of the real world.
And how can it be, like, if existing is the criteria, where do you take into consideration that this molecule is going to be useful and in terms of medicine?
That's, at the moment so far, only in the training set, so you want to generate molecules that have similar properties to those in the training set, so you would control that by choosing a training set that has the sort of properties you're looking for. But what would be the eventual goal is to put this in a reinforcement learning framework where you could actually give it a score of the different properties you're looking at to optimize for the molecules you're generating, and then kind of have it going, feeding that information back into the model as you're training. But we're not at that stage yet. But yeah, should we? Okay, one last question.
What about adversarial approaches? Adding a discriminator or
We haven't done that yet for graphs, and I know that there has been work done using GANs with molecular strains. So if you search in the literature, you will find a few different papers, and it seems to work as well. But yeah, maybe we stop questions, and if you have any further questions, you can find me at the Lingo. Thank you so much.